to be able to visit. Oh, yeah. Sorry. I hope now it works. Oh, yes, this work I'm going to present was done in collaboration with Ingo Schienbein, Lorenz Latore, and Björn Herrmann from Grenoble University in France. And I want to convince you that one can express a complete Two-Higgs doublet model in a gauge-invariant form, and I hope more insight into the model. So, as we all know, we can't see the possibilities sometimes. And in physics, this means that we know that you all know that the gauge symmetry is hidden after electroweak symmetry breaking. And the principal idea I want to show is to keep the gauge symmetry manifest. And let me show you what you all know from the standard model, how it looks like there. There we have one doublet in order to cover the two fermions. I think basic idea of the Higgs mechanism. Here in the convention, we see upper component electrically charged and the lower one electrically neutral. These components are complex fields. And then one can, as you know, write down the most general standard model potential, just these two terms with respect to renormalizability and with respect to gauge invariant. There's nothing more we can write down. And then, of course, we can define one real bilinear K in this way, and then the potential looks like that, simply just replacing phi dagger phi by K, which we have once here. And of course, it's bilinear in the doublets, this K. And then we get this simple function, which on the domain with K, a real quantity, non-negative quantity, just by definition. And then we can see, for instance, electroweak symmetry breaking will happen in case we get an unbroken electroweak symmetry, in case we get a vacuum where K vanishes, and in case K is larger than 0, it can't be negative, we have a partially broken electroweak symmetry down to the electromagnetic symmetry, as you know, to the U1. This is obviously, we see that it's advantages to introduce this bilinear K. And as I said, what do we have achieved? We have a simple real potential. It's a polynomial of degree 2, because we have replaced phi dagger phi by one function K.
Are you thinking in something like a theory of composite Higgs?
No. I will not go into that. I will show, the idea is to show you how to proceed in this manner in the Two-Higgs doublet model, in general, in the N-Higgs doublet model, how to introduce these real functions and to get new insights for the model. This is the idea. Just by, this is here, just usually it's not done in this way, but we can do that, and we see that we have a real potential, and we can see how we can understand electroweak symmetry breaking easily, just as a motivation how to do it in the Two-Higgs doublet model or in the N-Higgs doublet model.
Is this equivalent to having just a vacuum expectation value of the phi different from 0? Is that equivalent?
Yeah, this is exactly. If you, of course, we get we break. You know, if you go to a vacuum where we had for the neutral component the physical vacuum we want to have usually is that we have just for the neutral component a vacuum expectation value and in neutral vacuum, and for the upper one we get 0, and in this case it corresponds to K larger than 0. And in case we get a where everything vanishes, it's a complete field vanishes, then K vanishes, and then we have the unbroken electroweak symmetry. Just the idea is here is just to replace phi dagger phi, these doublets, by K. and then discuss the Standard Model in this way. Without, where we have this K is manifestly gauge invariant. This is under gauge transformations, this is invariant, doesn't change at all. Transform trivially. So we have maintained everything gauge invariant, which we in this case also see here directly in the potential state. It's of course formulated gauge invariantly, but we never go to a vacuum where we put phi 0 to a VEF. We don't hide this. What I want to say is we don't need to hide the SU2 cross U1 symmetry, the electroweak symmetry. This is all I wanted to say. This is the second statement, that the symmetries are not hidden by unphysical gauge degrees of freedom. We don't go to compare that where we go to a VEF where the neutral component gets a vacuum expectation value, and we expand around this VEF, and then everything, if you plug this into the potential, it gets easily a mess. You know, we get many terms and all of them. We don't see the gauge symmetry manifestly, and we are, as I want to show you, we are hiding lots of information. Let me show you how we do this in the Two-Higgs doublet model, and in a similar way also in N-Higgs doublet model or other different extensions. The basic idea is this was done in '94 from this Lisbon group, where instead of the doublets, these four quantities were introduced, real quantities. They were called x1, x2, x3, and x4. But then later in Heidelberg, we introduced these quantities for the doublets in this special way, K0, K1, K2, and K3. And then we can show that there's a one-to-one correspondence between the doublet fields in this case. These are now these bilinears I want to talk about. We instead of talking about the doublets, we talk now about this case. And there's a one-to-one correspondence. How do we get to this special form, K0, K1, K2, K3? This is just if we build this matrix out of the doublets, all possible gauge invariant terms, phi 1, dagger phi 1, phi 2, dagger phi 1, phi 1, dagger phi 2, phi 2, dagger phi 2, then we can decompose it in the basis of the Pauli matrix and the unit matrix, and these coefficients are just these bilinears. This is the way we get these. But it doesn't matter. We can construct this case and talk, instead of the phi's, we can talk about this case. And
how do you give masses to the fermions?
I come to that. Yeah, exactly. All this is possible in the gauge invariant way. I come to that. Yes, I want to convince you. These, by construction, these bilinears.
Excuse me, may I ask a question?
Yeah, of course. Please.
Please go back to one page. So the definition for K0, 1, 2, 3. Here is what your motivation to connect the pi 1, dagger pi 1, and the other terms with the K's. So what is your motivation?
The motivation is, as we see, that we are only talking about gauge invariant quantities, and there's a one-to-one correspondence between this. I will come to that. You will see how simple everything gets if we do that. You will see everything is real. These are real functions. First of all, these are real functions, and we can see how simple the potential becomes. The Two-Higgs doublet model, or even the N-Higgs doublet model, the N-Higgs doublet model becomes very, very accessible. You know, you have in the Two-Higgs doublet model, you have this lambda 1 to lambda 7 terms, and then you have the 3 mass terms, and everything is complex and not very easily to find, for instance, stability, electroweak symmetry breaking, to discuss general symmetries like CP or any other symmetries, and everything will become very, very accessible and easy.
Okay, thank you.
I will, of course. Please, always interrupt me, please. For instance, as I said, by definition, this case, which replace now phi 1 and phi 2, these two doublets, live in this domain. It is just if you think about K0, K1, K2, and K3, this is a forward Lycon region somehow. if you want. K0 is a forward light cone. If you choose good enough like that, these are real functions and they are defined on the forward light cone region. So what we do, I will show you, we replace the potentials of phi1 and phi2 by these Ks. And then one can see that how the electroweak symmetry breaking looks like. For instance, in case of K0 equals 0, which is within the domain, of course, then if we will see the potential, it doesn't matter now, the potential vanishes completely. But this K0 was phi1 dagger phi1 plus phi2 dagger phi2. So if this vanishes, the doublets completely vanish. And so we see that we get an unbroken electroweak symmetry immediately. And then we get the charge breaking minimum. This is the region within the forward light cone, where this is just an unequal sign here. K0 squared is larger than, it's within the forward light cone. And the condition for the potential to fulfill this would be a vanishing gradient with respect to this case. And similar, we get on the surface of the forward light cone, we get the neutral vacuum, as one can see. Not shown in every detail here. But believe me, I can also explain it to you, but I want to go to another aspect, to focus on another aspect. So just these different cases can be easily distinguished. And the condition here to find this minimum from the potential is a vanishing gradient, where we have to take into account this forward light cone for the surface condition, for the surface, K0 squared equals this. The sum on the right-hand side is we get this condition. We have to take it into account. We are looking for a neutral vacuum. This is the neutral vacuum condition is this one. So we have to impose a Lagrange multiplier.
So far, this is a better way, a simpler way to analyze the scalar potential that the main upshot here.
All right. This is we are at this point. I will come to the complete model. The idea is to extend this idea to the complete model, not just to the potential. It's at this stage we are talking about, as to say exactly.
Marco, sorry, in your page 7, the I factor is present there or not in the definition of K1, or is a typo in page 7, the previous page?
No, there should be no I here.
No
that's
I,
right.
here should be no I.
There shouldn't be any I here. No, that's right. Here are the. Oh, thanks a lot. I haven't seen that. This is a typo. So the I appears in K2 only. Right.
Thank you, Mark.
Very good. So where is he?
Sorry, excuse me. Sorry, I have a question. So in the previous slide, once again, then they are written in terms of the polymatrices, right? The sigma I, are they the polymatrices?
What is this? I didn't got the point.
The equation K is equal to the matrix equation. So it is written a half of K0 I2 plus Ki sigma I. So sigma I, like one, it will have some factors of either, right?
Yeah,
so,
but it's real. This is real. This will be real. This comes from the, as one can see, that it's real, completely real. It's the I. It's a real function. And this way, it's constantly real. Cases are all real. Everything is real, as we will see. Just I wanted to mention that the right, because we need this later, the global, of course, the global minimum is determined now by this condition, which is in the lower line written, the gradient with respect to the case. And then we get a global minimum with respect to values of K0, K1, K2, K3, and U. We have to impose a Lagrange multiplier, as I said, in order to get the neutral vacuum. So as I said, I mentioned we can build a 4-vector, a Minkowski-like 4-vector of these Ks instead of the doublets. In this way, K0, K1, K2, and K3, we can write them if we like, we can write them like that, and then everything is a little bit more concise, I think. And then we can also introduce a dimensionless bilinear where we divide this vector copulence by K0 in case K0 is larger than 0. K0 equals 0, as you know, it's K0 was phi1 dagger phi1 plus phi2 dagger, but it means simply vanishing fields. This is a trivial case where the whole potential vanishes. And then here is shown the complete, most general Two-Higgs doublet model potential. In blue are the parameters, which is here are the k's. This is the k vector. K0 is one of the bilinears. And this is the k vector, k1, k2, and k3. And here we have in blue the parameters. This is a three-component vector. This is a scalar, eta 0, 0. And this is a three-component vector, eta vector. And this is a 3x3 matrix. Symmetric by construction, symmetric matrix. And everything is real. This is the most general Two-Higgs doublet model potential. One could add a constant, which we can always drop from potential, of course. And everything is manifestly gauge-invariant. But these bilinears are constructed in a gauge-invariant way. They're all constructed gauge-invariant. And everything is real. The potential is real, and the parameters are all real. We got here 14 parameters in total in the Two-Higgs doublet model. This is the idea. And let me show what is the advantage. So now we have to introduce something, and we have to see what do we gain from that. And we will see. I hope I can show you quite a lot. For instance, there's lots of discussion about basis transformations. We have, of course, two doublets in the Two-Higgs doublet model, and so they carry the same quantum number, so we can consider any unitary mixing of the two doublets. And if you do this and write down the new potential, it looks very differently usually. But you can see that if you do this and now do this with a potential written in terms of bilinears, this basis transformation is just a rotation of this k vector. Actually, this k0 is kept invariant by any unitary transformation. And this k vector, k1, k2, k3, is just rotated. So you can easily detect any basis transformation. You see that in different papers in the literature, you see several potential, many, of course, there are many, there's a lot of discussion of the Two-Higgs doublet model. I didn't introduce, of course, we want to have the main motivation was given by T.D. Lee to get another source of CP violation, and this is up to now. Of course, it is a viable idea to introduce two doublets instead of one, where we can have CP violation. And then here I want to show you how we can treat these models in a concise way. And you find lots of discussion about Two-Higgs doublet models, of course, and you can see that many models which are just related by basis transformation. Yes, you can easily detect if you transform for instance, here is the potential to bilinears. This is easily done. You start just by these relations, and you inverse them. You can add these relations and subtract these bilinears, and in order to get to single out this phi I dagger phi j terms, and then you can replace them, and then you have the potential written in bilinears. It's very easily done. You get the potential automatically in this form, and then you can see whether or not two potentials are related by simple basis transformation.
But so far you haven't broken the symmetry. You haven't chosen the vacuum state, nothing.
No, nothing broken yet. No, right. This is an electroweak similar. I come to that. Would be just by minimizing this potential, and this would be done by solving these equations. And this can be done, of course. This can be done. We have also shown how to do that, and this can be done to find the global minima. Also, you find all the minima. You find all the stationary points. Actually, first you have to study stability. We have given the conditions to study stability in the most general case, also for the N-Higgs doublet model, actually, and then you can, of course, it doesn't make sense to study electroweak symmetry in an unstable potential that's bounded from below. So you first have to check the potential is bounded from below, and then you find all the scenario equations, and among them, the deepest solution is the global minimum. Then can you see that it has the right electroweak symmetry. Let me show you another example. For instance, CP symmetry, the basic motivation to go to Two-Higgs doublet models, which are in the standard CP transformations, is defined in this way, where you have this parity of the argument. These are the doublets again, phi 1, phi 2, are the two doublets, and then written in one equation. Under CP, we have a complex conjugation due to this charge conjugation, and the parity transformation is given here, flipping the sign of the spatial component, right? This is the usual CP, standard CP transformation of the doublets. And one can see that in bilinears, it's just flipping the sign of K2. It's just, everything is real. It's just flipping the sign of K2. So you can easily see whether Two-Higgs doublet model is CP violating or not, just by the simple transformation. Just an example, which is much more complicated in the case you deal with doublets. There are thousands of conditions which were given by Haber many years ago, if you have to check. And this is very simple and very simple, because everything is real and it has this geometric meaning, just as a reflection on the 1-3 plane. And it's very easy to detect CP transformation anymore. Another example, and you can go ahead and study any symmetries and in Two-Higgs doublet models. But up to now, there's some drawback. We have only studied the potential, as you mentioned. The question arises, how can you study gauge couplings, Yukawa couplings, like the masses of the fermions from the Yukawa couplings, of course, or the potential beyond tree level also. And I want to convince you, this is actually the main part, that one should start, or the idea is, the key to achieve this is to study the mass matrices from the beginning in a gauge-invariant form, and derive the couplings from the mass matrices. And this is what we did recently. And because the mass matrices are defined with respect to the component fields of the doublets, I need to bother you with some technical details. So again, these are the two doublets we see in the convention. We see upper electrically charged. And then we can, of course, these are complex fields, so we can decompose these two doublets in terms of real and imaginary parts, where we have this conventional factor in front. And then we can collect all these components we have. These are 8 components, these 8 real components, into one vector, if we like. These are general complex fields, so we can write them like that. These are the 2 real parts of the first doublet, the 2 imaginary parts. Where this 1/√2 is always missing. There's 2 imaginary parts of the first doublet, and the same for the second doublet. And this is now a real vector. We have decomposed it simply into real imaginary parts. And so the mass matrix is defined in terms of these component fields, now written in this way: the second derivative of the potential with respect to these component fields. I and J are these components. It's an 8-component vector, of course, and the 8 components. And this is the mass matrix, squared mass matrix in terms of the component fields, how it is defined. And we want now, since we want to go for gauge invariants, to formulate the mass matrix in terms of bilinears. So these are, because they are intrinsic gauge invariant, this is the index from 0 to 3, and Koski-like. And then this condition for the mass matrix in terms of would read like that. The question is, how do we get from this to that? So here we have a gauge-invariant form, and we have here this, obviously this depends heavily on the gauge symmetries. If we apply rotations, SU2 cross U1 rotations, they mix, all these components mix in a complicated way. So this is completely gauge dependent, appears to be completely gauge dependent. And here we have expression which is completely gauge independent. And actually we would expect, and this was the basic idea, we would expect that the mass matrices are physical quantities. They give the masses of the model. So we expect that this quantity finally should be expressible in gauge invariant quantities. This was the basic motivation for us to study this, because any physical quantity cannot depend on any gauge under gauge redundancies. It's unphysical, of course, and so any physical quantity cannot depend on them. So we expect that we finally can express this mass matrices squared in terms of gauge quantities. And then here's some technical details how we did that. So we know this bilinears we have seen, K0, K1, K2, and K3. This is the index mu running from 0 to 3. Bilinear in the doublets, and therefore they are bilinear in the component fields. If you write them explicitly, you can see that in terms of the component fields, they are also bilinear. And so we get some constants here. For every bilinear, we get a constant here. And this is actually every constant here is an 8 by 8 matrix. We have expanded the bilinears in terms of the component fields. We can explicitly do that. I can show you that, but there's too many technical details. I was thinking at least. And so we can expand them like that. This is now, I want to show you how we get from this mass matrix in terms of component fields to the mass matrix in terms of bilinears. And this will give new insights I want to show you. Unexpectedly deep insights I want to show you. So, and what is the connection? Here's a connection between the components to the bilinears. So we build the derivative of the bilinears with respect to the component fields. And then we get from this expression directly the result. And then we can apply the chain rule, just the derivative with respect to the component fields corresponds here by the chain rule, simply by this connection times the derivative with respect to the bilinears. So this is a translation, this allows us to translate derivative in a gauge-dependent way to here we have this mu index, which corresponds to the gauge-independent quantities. I, of course, corresponds to the component. And then we can apply this to the mass matrix squared, and then we get immediately the translation. And we can write it. I don't want to show you too many details. Just we get the translation from this matrix, from this squared mass matrix of any Two-Higgs doublet model, which we don't have specified anything. We don't have specified the potential. It's just V, and then we can translate it to this gauge-invariant format. Here appears exactly then this matrix, which we want to have. And we can write this in matrix notation, suppressing this indices I and J. Then it looks like that. This is a connection, and these are these constants. And then we can, as we show in our paper, we can go to a basis where this connection is very simple, and we can diagonalize this matrix. And then we find this striking result, I guess, where we find that the mass matrix squared looks like that. And now it comes the charge part. We get immediately, we see that we immediately get the 3 Goldstone modes, as we have to have for the neutral minimum. Here we use, in order to get that, we use that the conditions for the minimum, right, for a neutral minimum. And then we immediately get the 3 Goldstone modes in a transparent way. We get the charge part of the mass squared matrix. It looks like that. We see that the charged Higgs boson masses are simply given by the minimum. And this we get without specifying the potential nor of the model. So in any Two-Higgs doublet model, this means from the minimum, we get the charged Higgs boson masses immediately. For any Two-Higgs doublet model, even at any order, even in effective models, it is just the Higgs boson, the charged Higgs boson mass is simply determined from the minimum. This we found remarkably without specifying the, as I said, the model. It has just to be a Two-Higgs doublet model at any order, at any even an effective model. And also here some details. This is the neutral mass matrix, how it squares the neutral part, how it looks like. This R comes from the diagonalization, and this gamma 3 is given here. Everything gauge-invariantly. Of course, as we expected, we can express this squared mass matrix gauge-invariantly. And this is, you know, we learn in school to go to the, it looks so easy to go to the neutral minimum, where we get typically in the literature, the stability is not checked thoroughly, at least, or if you check it in some special cases, and you go to the minimum and you expand around this minimum, but then you hide everything. This is the biggest mistake, I would say. So therefore, this is difficult to see without with hiding the gauge symmetry. Here, as we get in a transparent way, everything very directly, very concisely. As I said, the Higgs boson mass squared at any perturbation order in a direct way, and also the masses of the three scalar Higgs bosons we get immediately. Yeah, and any two-Higgs doublet model, we have 5 Higgs boson masses. Of course, we have H degrees of freedom. 3 goes away from electroweak symmetry breaking from the 3 generators, and so we have these 5 H plus, H minus mass, and then we have these weak scalars. And here we can compute them. And as I said, we haven't fixed anything. We haven't fixed the model at all. And this motivated us to, as I said, what have we found? We have kept the gauge symmetry manifest all the time, because we are dealing with bilinears, which are gauge-invariant quantities. We haven't specified the potential, and so we get the charge Higgs boson mass like this, just from the minimum. And as I said, this is a relation which holds in a very general way. But here's some. But up to now, we have only considered the potential, but we can go ahead and also study the rest of the model in a gauge-invariant way. And let me just briefly mention how we do that, just to get an idea. As you know, this mass matrix squared was the second derivative with respect to the competence fields, and here we get the third derivative of this squared mass matrix, which corresponds to the trilinear couplings among the Higgs bosons, right? And then we do the same game. We translate it to gauge-invariant quantities, and then we get again this mass matrix in terms of bilinears, and then we can compute all these quantities and get all these couplings. And they are manifestly gauge-invariant, as you see here, for instance, the scalar charge Higgs boson pair of the trilinear coupling of a pair of charged Higgs bosons to a scalar Higgs boson is just given by this quantity. Where in blue are the parameters of the model, and these k's are gauge-invariant quantities. These k's divided by k0. So gauge-invariantly completely. And these are the masses. MA are the masses of the, this is the mass of the 3 masses of the scalar Higgs bosons. Well, we can express everything gauge-invariantly. And also one could ask, this was your initial question, this sounds strange, but it's also possible, because, you know, if you go to the Yukawa sector, here's an example for a Yukawa sector, the basic idea of the Higgs mechanism, to get masses for the fermions without violating any symmetries. And yeah, as you know, this is done by the Higgs doublet coupled to fermions. QL is a left-handed doublet, and U, right, is a singlet, the fermion singlet, and this is a conjugate doublet defined. And this way, the usual business. And then you think, of course, what can we do here with bilinears? They are bilinear in the doublets, but this can be done easily if you remember that these bilinears, this was the initial matrix defined, has to have, one can see for a neutral vacuum, has to have rank 1. And this means we can decompose it in terms of 2 vectors, kappa, and then express these gauge-invariant vectors, and then we can express these Yukawa terms in terms of these kappas. Just here is shown as an example for one specific coupling of the Higgs. And of course, from that you get then the mass of the particle. This is just these are the couplings, the Yukawa couplings written in terms of 1 vector. And then you get explicitly you get the Yukawa couplings. And as you expected, you have to do this trick. There's no problem at all, because for the neutral vacuum, as I said, you can linearize it by bilinears in this way. And then everything can be done. And this already brings me to the conclusion. We have computed the mass matrices in any Two-Higgs doublet model for all orders. We haven't specified the potential, as I said. We could extend this formalism to the Yukawa sector, to the complete scalar sector, and the gauge-boson couplings. And we hope that we have in this way completed this program of bilinears. And what we are actually doing is we applying this to effective potentials to higher orders, to show how we can get new insights and new results from this formula. Yeah, thank you very much for your attention.
Thank you very much, Markos, for the very nice talk. There are questions from the audience. Carlos, please go ahead.
I was agreed. I would like to ask you only you calculate this in one loop approximation.
Yeah.
Is this in the same, or because you can start on with all the transformation?
No, this would be actually this would be the same. This is also we are working on that actually to show because we for instance, first of all, for the charge Higgs boson mass, you get immediately the result. And you have to find, of course, the global minimum. So you have to minimize the potential in order to get this K0 in the Lagrange multiplier. And it depends also this also depends on the renormalization scheme and everything. This is inside of the minimizing potential. But you get immediately the Higgs boson mass, and you can see that you also get all the other masses. And for instance, in this H bar expansion, you can do that. This is how we are working on that. It's an X bar expansion, writing down the effective potential and computing all the quantities. This is
okay.
This works.
More questions from the audience? Alfonso, go ahead.
Thank you. Thank you for the very nice talk. I'm curious if the formally as a geometrical interpretation in terms of the manifold of the group, for instance, of the gauge group.
This is of course you have the connection of U2. This, for instance, is basis transformations. U2 transformations, and these are mapped to SO3. So these rotations here, for instance, you change your in terms of doublets. You have this U2 gauge transformations, U2 transformations, the mixing unitary mixing. For instance, this would correspond to SO3 rotation, and we studied also symmetries, which have to be arranged such that the kinetic terms are not violated. And then we studied all the classes of possible gauge groups. We have classified them and done that. This is exactly as you say. This is and you get a very geometric meaning of all these transformations. Because, for instance, here you see just as you said, it's CP transformations are just a plane transform. Is this plane transformation in the 1-3 plane? We get geometric meanings, which you don't see before, of course.
Yeah.
Hidden. And this bilinear formalism was independently. And by us in the hypergroup, it was also independently developed by Celso Nishi from Brazil, from Sao Paulo. At the same time, we were at the same year we published these ideas, but I didn't say that. So we published that, and he also and it's with different notation, but exactly the same idea.
Okay, I have several questions. The first is how do you do calculations here? First, how do the W's and get their masses? It's not clear to me.
Yeah, from the kinetic, yeah, in this term, of course, the W's get the mass from the kinetic terms, and you do this calculation in terms of bilinears, strictly.
Yeah, but where are the gauge-bosons and everything? I mean,
everything comes out correctly, I hope. The Goldstone bosons appear here already. We immediately get the Goldstone. This is a mass matrix in terms of gauge-invariantly formulated. We get immediately the 3 Goldstone bosons, as it has to be, of course. In the neutral case, we get this. This comes out from the formalism in a much more transparent way, I must say.
The other thing is, how do you do calculations here? Because your fields are no longer propagating fields. I mean, at least they are different. How do you do? How do you do calculations? I mean, perturbation theory and everything. These new fields.
No, this is all possible. Simply, you just have to switch from if you start, for instance, for the potential is just to use these relations. All right. Yes, I have seen to use these relations, invert them.
Okay, you can work with the potential, that's fine. But I'm talking about doing sort of perturbation theory calculations.
Yeah.
You need the fields. I don't think with this sort of bilinear, it's not the same.
You have this it's actually it is the same with. In the sense that, but it's not the same. It's the same except from gauge transformations, of course, because the other expressions depend on the gauge and these don't. This is the difference, of course, and this is the whole idea. But then you get, for instance, for this coupling, you get this expression, and then it is just here the masses which follow from the squared mass matrices, as I showed before, and you get this coupling. And then you have your, as you said, your propagators, and you construct your loop calculation. Everything can be done. There's no problem at all. This is not, it's manifestly gauge-invariant, as it should be. I guess what hides everything is this usual, just what we learn in school, to go from the doublet to the minimum and expand around the minimum. And this hides everything. And this we don't do. This is the main point. And then everything appears quite transparently. And of course, if you have the couplings, and as you said, you have the propagators, and you can do the calculation.
Markos?
Yeah.
Sorry, a very short question. The idea is try to investigate first the potential and then try to do the transformation for the general action. But what's happening with the propagator? The propagator is diagonal, or is you have to finally you go to another approximation from randomization group or whatever you want in order to study general property? The propagator is diagonal or not in this new variable?
First of all,
probably is gauge invariant, totally agree.
But no, diagonal, propagator is diagonal. What do you mean, diagonal with respect to what?
No, I assume that probably if you go to one of these minimum from this potential, you have to do an extension around this, of course. Yeah. But when you try to do perturbation theory, you are assuming that the structure is more or less when you diagonalize in the masses, I assume. That is the same that you diagonalize all the kinetic term. That means the q square on the mass. That means it's diagonal.
Here you have diagonalized this. The mass matrix is diagonalized, for instance, here, right?
Yeah.
So we have.
No. I understood.
Yes. Yeah. And then this is just explicitly expressed engagement quantities. You not necessarily would have to change the propagators. You can go ahead also with the propagators if you want in any form. But then it would the expressions finally would depend on what is usually done is you go to the effective potential, right?
Mm-hmm. Yes, of course.
You get this log terms and then of course at one loop this would be one loop approximations, and you would expand it around if it's for this H bar expansion. But maybe I don't get the point. So you can do it before all the calculations. So it's simply we have expressed the couplings and the masses. Everything can be expressed in terms of gauge-invariant quantities.
Mm-hmm.
And then you can go ahead and do all the calculations as before.
Okay.
Just for instance, we can, and in this way we have seen, for instance, that we get very concise expressions which don't hide any gauge symmetry. It's not hidden by any gauge. For instance, the charge-Higgs boson masses, it was somehow a surprise for us. In this general form, we get the charge-Higgs boson, or even the other masses.
Okay.
More questions from the audience? If not, we send Markos Maniatis for the very nice talk.
Thank you very much. Thank you very much.
Thanks a lot, Markos. Thanks a lot for the very nice talk. And we meet at the next seminar. Bye.
Okay, bye-bye.
Bye.
Bye.
See you.
Bye.
See you. Bye.
Bye.
Bye.